We're going to work through two unbalanced force diagram problems. In this scenario, a man pushes a 100 Newton stroller and he pushes with a force of 30 newtons, and the friction between the man and the ground is 44 newtons. The mass of the man is 70 kilograms and you need to figure out what the acceleration is. So let's start with putting the information down of the man. I think we've got quite a bit over there, so that might be a good one to start. So the first thing, we know that the man has a mass of 70 kilograms. In that case, we know that 1 kilogram is 10 newtons of force, and that means that the gravitational force between the man and the Earth is 700 newtons. At the same time, let's just do the interaction diagram. We know that the man and the ground have an interaction. The man and the Earth do. Man and the stroller and the ground, stroller and the Earth, and ground and the Earth. So we also see that the ground is pushing up on the man, and in this case that pushing force is normal force between the man and the ground. And we're told that he pushes the stroller with 30 newtons of force. So remember, it's about what this man feels. If he pushes the stroller with 30 newtons of force, he feels the stroller pushing back at him. And so for that reason, the vector is going to be to the left, a normal force between the man and the stroller, and that's 30 newtons. It also tells me that the man and the ground have a frictional force of 44 newtons. I need to make certain to draw that nice and a little bit longer, and that has a frictional force between the man and the ground. Over here we have the normal force of 700 newtons. So this will actually help us in identifying what this acceleration is of the stroller. So first of all, we can tell that while these two vectors are balanced, these two are not. And when I look at that, I can circle my unbalanced, it looks like there's a difference of 14 newtons. So we know that our net force is 14 newtons. Let's see if I can use the acceleration of the man to figure out what the acceleration of the stroller is. So we have the man here. So I know that F net equals MA. I know that the mass of the man is 70 kilograms and that we have a net force of 14 newtons. I need to find my acceleration, that's my unknown. So what times 70 equals 14? Well, if I divide 70 into 14, I determine that my acceleration is 0.2 meters per second squared. And we're going to make the assumption that if he's accelerating 2 meters per second, 0.2 meters per second squared, then the stroller is accelerating as well. So let's put in what we know about our stroller to create a force diagram. So for the force diagram, we know that the stroller has 100 newtons of gravitational force, so that's going to be a smaller vector. That is between the stroller and the Earth, we have 100 newtons of force. And the ground is pushing up on that stroller with normal force between the ground and the stroller, and that is also 100 newtons of force because he's not moving up or down. Then I also know that the man is pushing the stroller with 30 newtons of force. With 30 newtons of force. So that's going to be 30 newtons right here. The stroller is being pushed by the man. All right, so we have a third law force pair right over here. So now what about frictional force? We need to get an answer for this one, but we don't know what it is. But we can find it out based on net force. So let's start with what we know. We know for the stroller that the stroller is traveling 0.2 meters per second squared. And I know that because the man is traveling 0.2 meters per second squared, and they're moving together, so that's for that reason it's accelerating at this rate. I also know that the mass of my stroller is going to be 10 kilograms. I know that because for every 10 newtons of force, it is 1 kilogram that's responsible for that, so that's my mass. And now I simply can plug it into my F net equals MA formula. So 10 kilograms times 0.2 meters per second squared works out to be 2 newtons of net force. Remember, that's the difference between the two. And because I know it's accelerating in the positive direction, that tells me that my frictional force is going to be 28 newtons, because 30 minus 28 is 2. And this is force of friction between the stroller and the ground. So what are the third law pairs between man and stroller? We know that the man is pushing the stroller is pushing back on the man. Does the man or the stroller push with more force? They push with the same force because they are a third law Newton's pair. How far does the stroller move in 3 seconds? Well, let's go ahead and look at our times here. We have, let's fill out our velocities. I'm going to put it on pause. So if I can complete the time and velocity and position time graph, you should get to see data like this. Just a reminder, remember it's accelerating 0.02 meters per second every second, and we want to find what the average speed is between each second interval. So between the 0 and 1 second, the 1 and 2 second, that's my averages right over here, and those averages we add on to our position from that. So how far does the stroller move in 3 seconds? We would say that it moves a total of 0.9 meters. Okay? Let's work through the next one. So for the next one, we have a hand that's pushing up 3 blocks, and they accelerate at 0.5 meters per second squared, starting at rest. And we have block 1 that has a mass of 1 kilogram, block B that weighs 20 newtons, and the hand that pushes up with 63 newtons of force, block C, experiences a net force of 1.5. So I want to essentially know what the mass of my box C is, and I want to know third law force pairs. And we can do this all by looking at our force diagram. So let's start with the easiest, well, let's start with an interaction diagram. And we have the Earth over here. We have A and the Earth, B and the Earth, and C and the Earth. And we also have the interaction of A and B, B and C, and C and the hand. Okay? So for block A, the only interactions I see are that of the Earth and of block B. So I know I have at least 2 vectors. So here's block A. So what is the Earth doing to block A? It is pulling it down with a force of gravity between A and the Earth. And it looks like block A weighs 1 kilogram, and so for that reason I know it's with 10 newtons of force. Now the thing is I notice that it's accelerating up. So I am not certain. I know there's a vector up because A is pushing up. B is pushing up on A, but I don't know with how much force, because remember it's saying it's accelerating. It's not moving at a constant rate. So let me use this workspace here to figure out what the net force is. So I do know that that block A is accelerating at a rate of 0.5 meters per second squared. So this is for block A. I know that block A also has a mass of 1 kilograms. So in that case, what is the net force? Well, I know F net equals M times A, and then in that case, I simply multiply my 1 kilogram times 0.5 meters per second squared, and I have a net force of 0.5 newtons. That means the difference between this value and this value has to be 0.5 newtons. So I do know I have an upward push. That's a normal force between that B is pushing up on A. And remember, thanks to my net force, I know that the difference has to be 0.5 newtons. So that means it must actually have 10.5 newtons of pushing force up. So the difference is then 0.5. Okay, so for block B, let's work through this one here. Block B, I know I have, again, a gravitational force between block B and the Earth. And up here it tells me it has a gravitational force of 20 newtons. I do have a force pair over here. I know that if block B is pushing up on block A is pushing down on B, and it has to be with the same amount of force. And so I create a shorter vector where it is a normal force between block A and block B, and as I have over here, I know it is with 10.5 newtons of force. Now the same scenario, I know that block B is also accelerating 0.5 meters per second squared. And I also know that its mass looks to be 2 kilograms. Remember, for every 1 kilogram we have 10 newtons of force. And if I multiply these two together to be 2 kilograms times 0.5 meters per second squared, I get a number of a net force of 0.1. So I know my net force for block B is 1 newton. That means the difference has to be 1 newtons. This works out to be 20 plus 10.5 is 30.5. So if the difference is 1, this has to be 31.5 newtons of force. And this is a normal force between block B and block C. And that gives me that 1 newton of force difference, that net force. All right, so now we have block C. Block C, it tells me, experiences a net force of 1.5 newtons, and I can also know that the hand pushes up on it with 63 newtons of force. So let me work on that first. I know that the hand is pushing up C, and it has 63 newtons of force. I also know that B is pushing down with 31.5 newtons of force. That's my third law force pair. Okay, so now the big question is, well, what is this value? Again, because it's accelerating, I actually have to figure it out using F net. And I know that it tells me that F net for block C is 1.5. I have an acceleration, because they're all accelerating at the same time, of 0.5. And if I do my calculations correctly, that means my value of m, if I divide 0.5 into 1.5, is 3 kilograms. This tells me that my Fg force, remember 1 kilogram equals 10 newtons of force, is going to be 30 newtons. Am I correct? Yes, exactly right. All right, so that allows me to figure out the mass of box C. All right, I'm going to pause and fill in the. So once I plot this data, you'll notice that for my velocity, I've increased the velocity 0.5 meters per second each second, and the average velocity is what I've added onto my position and time graph.